this field, we specialize in simulation for plastic injection molding, which is part of today's topic, computational flow dynamics, and finite element analysis services. So these are software that performs simulations that reduce the need for actual testing, and you can predict a product's failure in real-world scenarios. So with these predictions, you can reduce cost and waste during your design and manufacturing. And under the make, we provide CNC post-processing, and a very popular technology these days, we offer 3D printing services. So lastly, under application, we cover both software and hardware implementation, and we customize training of software and systems, and we do product data management solutions. Next, please. So over the years, our clientele have expanded, and our customers are from a wide variety of industries and segments, as you can see. So you can see some of this. We have government agencies, Institute of Higher Learning, research institutes, oil and gas, semiconductor, electronics, plastic injection, molding, consumer products. So this is where we have been offering value driving and end-to-end solutions to these customers. Next, please. So this wraps up our introduction. So you can always visit our company website, or you can contact me to read up on our full range and solution. So thank you, Suton, and I think you can allow you to carry on the rest of today's topic. Thank you.
Okay. Good morning, everyone. I'm Suton from Solution Consultant from I-VTech Solution Thailand. So today we're gonna talk about how mold cooling improve part quality and cycle time. So if you have any question, maybe after finish the slide, and then you can ask or typing the question in the chat box. Okay. Today I'm gonna talk about 4 topics: the basic cooling and the cooling with Autodesk Moldflow, conformal cooling versus conventional cooling. And the 4th topic is the conformal cooling in AMI 2021 CFD for cooling channel. So we go start from the basic about cooling first. Okay, why optimize cooling? Cooling affect quality. We have 4 topics about surface finish, residual stress, crystallinity, and the thermal bending. What are they mean? I will explain about in detail in the next slide. So the cooling affect production cost, the part temperature at injection, and the cycle time. We focus on about the cycle time because the cooling consume much time at the percentage in the pie chart. I will show you next slide. But I want to emphasize this: the proper cooling. If we do the proper cooling, we will get the better part in shorter time. If we do the poor cooling, the poor part in longer time. We can see from the difference in the picture. And then on the right side, we have the cycle time reduction from 40 seconds to 31 seconds, so that we can reduce about 9 seconds per piece. That's quite effective amount. So in detail, the surface gloss is many materials require relatively high mold surface temperature to achieve a great surface gloss. This is the keyword. So the residual stress as well. Residual stress is the result of the shear stress during filling and pressure holding. I assume that everyone know about the injection process. So to reduce the residual stress, so we have to do the uniform cooling is required. This is the keyword for this topic. So the crystallinity, so you see the injection process of semi-crystalline material influenced by the cooling of the melt. This is the keywords as well. So, and the thermal bending, the part will bend during the due to the different thermal shrinkage rates between the upper and the lower surface, that we have to reduce this effect so that we can get the result, good result of the part. What does it mean about the injection temperature? The injection part is ejected from the mold affected by many factors. The strength of the product must be large enough to resist warpage. The warpage is a problem of the injection as well. So due to the changes in volumetric shrinkage and residual stress, so you can see that's like a chain effect from the residual stress. Okay, and the cycle time, we emphasize on this because this one affect our price of the part and the injection cost as well. So we can see that the cooling time typically account for 80% of the cycle time. So if we can reduce this amount of percentage, we can getting more profit. Okay. This pie chart can show you, you can see that the part cooling start from the close the mold and fill the mold and pack and hold, and then part cooling. You can see that the clean area taking more than 50% of the cycle time that we should focus in. Okay, and this slide as well, we can see that the contact time have the injection time, packing time, and the cooling time. We want to focus on this cooling time, that if we can reduce this, we can get more profit. Okay. And this picture showing the heat in from plastic when injection into the mold. And then you can see that the heat out by convection, by radiation and plating. That are not enough. So we have to force the coolant into the mold, such as water or something, heat in or out from cooling line. And then this chart showing the raising mold temperature increase the cooling time. You can see from this is the PA66, PP or ABS. I focus on the ABS. So for example, if the mold temperature about 60 degrees centigrade, you can see that from the chart, we will get about 12 seconds of cooling time. If we increase that to about 80 degrees centigrade, we can see that's about nearly 25 seconds to cooling time. That's quite effective amount of time. And influenced by the thermal property of the mold material as well, 29 to 42. In case of tool steel P20, the thermal conductivity and the specific heat and the density as well, that we should concern about this. And the spacing between cooling line, you can see that many factors affect about the cooling system that we're gonna do. You can see that if we use the non-uniform heat removal, we should get something that's not quite satisfied, but more uniform heat removal is quite effective, but many factors have to concern. And the flow rates as well. You can see that the temperature gradients from the, if in the left side, the laminar flow, the Reynolds number less than 2300, and the right side is turbulent flow, the Reynolds number more than 2300. And we want to do the turbulent measured by the Reynolds number 2200 represent the onset of the turbulence in the water. Flow rate should achieve Reynolds number more than 10,000. That's the chart will showing the comparison between the channel diameter and the lead per minute at 25 degrees centigrade, and the 50, you can see that the temperature also at a factor. So many factors that we have to concern. So to get rid of all the factor complexity, so we go into Moldflow, and then we can knowing about how to calculate all of this by easier by the Moldflow tool. The cool solver in Autodesk Moldflow, we can separate into BEM and the FEM. The BEM is also, we can available in Advisor and Insight, but for FEM, we can do only in Insight since release 2012. And finite element method, the FEM, what does it mean? It means that more temperature option, average within cycle time like BEM, transient within cycle. transient form production startup. The left side is showing a mold temperature distribution and the mold temperature within a cycle. You can see from this graph, and then the mold temp stabilization. Okay, in this video, I'm gonna, due to the time is a factor, today we will talk about the theory and the showing the step, but I have to showing you in this because showing live may be taking time, and then it's not different. So please see this, and then I will explain about the process about selecting create mold mesh. We have I would like to know that everyone have the experience of Moldflow yet or newly. Please type in the comment to tell me. Okay, the process of using Moldflow is like doing meshing and then setting the boundary condition and the material. After that, we can check the free edge that no element were found that about the free edge. So we have to concern about the model. The model should be completely fixing the problem before sending to Moldflow, and after that we can cut the section in Moldflow to check the coolant, the cooling system, and see the result. Using the software is not complex, but the theory behind is more important, because after getting this you can see the result and translate into the human language. Okay. Okay, the process setting. The benefit of using Moldflow in the process setting, because once you select the material, the process is introduced by the system, and then you can adjust many things. Okay, after analyze the model, we'll get the result, and then we can cut the section to see inside the mold that we cannot see in the real life, but we can see in the software. And then we can answer the result and then see what happened in our model. Once we have Moldflow, we can reduce the cost to do the physical prototype, to testing many things. And after we get the result from the Moldflow, we go into the machine and we adjust something, and that's close to our requirement. You can see from this picture showing clearly about the temperature in the mold. Okay, rapid heating and cooling FEM. You can see from here the variable coolant inlet temperature and coolant during a cycle, heating phase and the air purge, and the cooling phase. The mold heating may be by water, steam, or electrical, or induction. Rapid heating and cooling benefits what? We can see that improved visual appearance. From the right picture, you can see the conventional molding. That's the surface is not gloss, but on the right side, for example, we use the ABS, for example, we can see that the right side, the surface glossy. You can see that a better surface quality. So visual appearance improve. And reduce veil line visibility. From the left side, you can see this area have a veil line visibility, but on the right side, can reduce the veil line. And the shorter cycle time as well, reduce warpage. Okay, the third topic we'll talk about the conformal cooling, that the main topic of today versus conventional cooling, what the difference. The mold cool traditionally, we drill the hole in the mold component and then using the joint plug, stopper plug, or inner plug to plug all the hole and then making control of the coolant to go inside the mold. Traditional, we use a lot of technique like a hot mold core usually cool down by more material with high heat transfer, such as copper, beryllium copper, or tungsten copper alloy. Spatial cooling channels, we use baffles, cost effective. That's on the left picture. But bubbler, more homogeneous temperature distribution. That's this one use the pipe instead. Can be produced by conventional manufacturing method. Because nowadays the rapid prototype is the price decrease, so we can it's affordable. So however, this strategy is not optimal and possible for all parts or all molds. So we have to concern about. Okay. The explanation about baffle and bubblers is like this. You can see from the left picture is baffle and the right picture is bubbler. A buffer is a cooling channel drilled perpendicular to a main cooling line with a blade that separates one cooling passage into two semicircular channels. You can see that the water flow like this. But the bubbler is different. The bubbler is similar to a buffer, except that the blade is replaced with a small tube. You can see the small tube. Coolant come in and then like a fountain. The coolant then flow down around the outside of the tube to continue its flow to the cooling channel. Like this video show you about the technique of cooling the mold nowadays. You can see from this video that's not effective much about the cooling. But the new technique is the conformal cooling. Maybe some people it's not new, but for some people it's new. So I taking that is it new. So the cooling channel of any shape, if you have the complex shape, you can see that if we can make the cooling channel close to the part, it quite effectively extracting the heat from the part. You can see from here. But the complex shape of the cooling channel have to rely on the powerful CAD system that Autodesk had invented and Fusion 360 that can help us to do the complex shape of the cooling channel. So, but the second problem is how to produce this. Nowadays, we use the RP rapid prototype. We use the selective laser melting technique because rapid prototype have many techniques to produce, but this one is quite effective because it's a functional part. So we use the laser to melting the powder of the metal and then combine it all together, and then we get the every complex shape we can produce nowadays. Don't worry about the undercut like a CNC machine. So we get the better quality, the reduction of deflection and the better surface quality. And we can do fast cooling, faster cooling, reduction of the cycle time, saving in energy. But the challenges is we require know-how to designing geometry that we have to attend the CAD course like a inventor of Fusion 360 before getting into Moldflow. But and the necessary and higher mold cost. Okay, that's true because doing complex shape, the cost also higher. But if we do the mass production, we can compare the price and then we can making the decision that we use technique and then is worth the money or not. Okay, and switch to conformal cooling. Why? Because continued pressure from OEMs to reduce product processing costs. That's the voice from the customer, and then pressure to make the this technique occur. So tier 1 supplier as well want to reduce cooling time, and it's contribute to 60 to 70% of overall cycle time. And the complex cooling channel following the path profile. Okay, the conformal mapping is nothing very complex to understand, because it's quite easy, because we want to do the cooling channel following the path profile. That's the keyword. So can be manufactured by 3D print, insert much faster way than traditional approach, and reduce overall tool development time. We can see from the picture on the left side, that's traditional one doing the cooling. We can see that we can see from the picture that's not effective way. But on the right side, we can see that the cooling channel flow along the path, that quite effective way to cool the path down and reduce the cycle time. That's quite a chain effect from the technique. And we can see from this video that the conformal cooling, we can see that quite effective way to extracting the heat from the path, you see here. And then the complex geometry in detail of the conformal cooling. The complex geometry of the conformal cooling channel can be incorporated into a cool FEM analysis. We emphasize this because if we do in the cool FEM analysis, we can do a lot of shape, and the more traditional beam element cooling system utilized in smooth cooling analysis do not adequately model conformal cooling channel, which closely follow the contour of a path. This is a keyword as well. A CAD model of the conformal cooling channel can be imported into the study and used in the cool FEM analysis. So that we have to set the cool FEM analysis in Moldflow to use this technique. The important thing that we have to taking care about, because the conformal cooling analysis can only be run on Windows system and are not supported on Linux platform. Any study can have more than one cooling channel, with individual cooling channel having either a conformal or beam element configuration. That's in detail of the conformal cooling. More in detail is individual cooling channel cannot be comprised of a mixture of channel type. So a section of a conformal cooling channel that have a beam-like appearance must still be modeled within a CAD package and treated as a traditional. Bubbler and baffle with a conformal cooling channel must also be modeled within the CAD package. So that we have to model in CAD package first. And then conformal cooling only use cool FEM analysis sequences, including transient cool analysis. And okay, in the last paragraph, I want to emphasize this because only part that used in dual domain or 3D mesh type can be analyzed within the 3D conformal cooling channel. Okay, we have to use this information. Okay, what is the selective laser melting? I can explain from the left side. We can see that's the powder delivery system. This piston will push the powder up, and then the roller will take the powder to the next chamber. And then we can see that the fabrication powder base is here. And once the laser directly shoot to the powder and it melt down, and then combine with the previously layer, and then we can produce the cooling channel in here. After that, the piston will push up, and then we get the part out of the bed. And then more in detail in the right picture, we can see that the sinter powder particle we call brown state, and then laser beam shooting to the powder, and then laser sintering. We call the laser sintering. The powder melt down and combine together to making the part. And then the unsintered material will be the support. so the parts not moving anyway. So this technique is quite useful for us to do the cooling channel with the complex shape. We can see from here, this type of shape, I will back to this one. Okay, you can see from this type of cooling channel, we cannot produce easily by the CNC machine, you see. But using the RP technique, nothing to worry about how many complex the part is. Okay, we can produce any shape by using the RP because it's making it layer by layer, so the undercut is not the problem. We can see this laser melting down the powder and making the part layer by layer. But the problem of the using the RP is a surface roughness, but we have to use the milling technique as well. So after sintering lamination layer by layer, we go into the milling process to make the surface smoother and then back to the layer again. Is it a repeating process? We can see the metal powder here and then the milling is here. Okay, we can see from the right picture first, the milling combined laser melting sintering. We can see that the precision is less than plus minus 10 micrometers, but the surface roughness also less than RZ5 micrometer as well. And then laser metal sintering, no milling. We can see that the precision is plus minus 100 micrometer. That's quite rougher, right? And the surface roughness RZ 150 micrometer. So this type of machine, Panasonic patented this technology and offer licensing to Masura Machinery Corporation. We can see from this video. The machines are producing layer by layer, as I presented before. After that, do the milling. Okay, and back again. Okay, let me see a comment. Please, okay. Fast delivery time for prototypes. For example, we use the lighting fixture pass prototype. For example, we can see that the core side and the cavity side, the core side, we use the laser metal sintering, and the cavity side slide core cutting. We can combine both technique in the mold, and then we getting the mold look like this picture, and then we can compare about the time, the percent and the process, the complexity of the process. We can see that the bottom is a conventional method. We use the CAD/CAM and then doing the electrode discharge machining, and then we do the CAD/CAM again for mold making process. But we use the laser metal sintering. We can use the CAD/CAM and then shaping the process and do post-processing. That we can reduce about 68% in production process. That's quite amount of number that we have to take care about. Okay, and reduce tooling time by 13%. So before we use the mass production mold conventional, we use the dual cooling channel, the cavity and the core. But after we use the laser sintering mold, you can see from the picture that the cooling channel getting closer to the part, and then that means every heat can extract easier and then faster. So we can compare from the left side and the right side. You can see the cavity part temperature 98 degrees centigrade, reducing to 94 degrees centigrade, and 103 to 100. So to summarize this, the part temperature declined about 5 degrees Celsius to about 27 degrees Celsius. So that's quite effective to our workflow. And the next benefit is the reduced warpage. The warpage is a problem in nowadays if we don't have the proper cooling. We can see from this, we need the warp correction process in the conventional cooling. We use the poor cooling and the bad warpage. We have that. This part is a bathroom ventilation fan frame. So it has the dimension about 215 to 256 and 136. And then we use the conformal cooling. We can see that we remove heat trap and then the parts less warp or not warp at all. So we can see this. This is the Japanese language, so I translate to overall view of the mold cavity design. We can see that this technique fairly worldwide, so we can see that in Japan, they use this technique as well, and then we can see the 3D model like this. Okay, to summarize, we separate it to 4 sections. The first section is CAD modeling. We can see that we have Inventor under Autodesk umbrella. We have Inventor and Fusion 360. And then the next process, we doing the injection molding verification by Moldflow. And then the third one, Autodesk also have the NetFab, the software that doing about the additive manufacturing. So this one is we have many software to help customer doing about the additive. The additive one is was about explaining the rapid prototype, but the CNC we use the subtractive technique. This one. Okay, we can see from the first area about the CAD modeling, we can see the Fusion 360 is quite powerful package to help us doing the conformal cooling design easier by the feature such as the coil. In this video, you can see we can cut, extrude, or combining the shape closer to the part easier. We can also do the surface modeling as well. So this one is quite effective because the price of the Fusion 360 is not high. So everyone affordable. And then we doing the return, and then we can combine all shape together to be the one part. And also Inventor can also do like this, but Inventor included in the PDMC product of Autodesk as well. It depends on what the user require feature. If the cost is effect, we can decide on Fusion 360's much cheaper package to do the 3D modeling. And then we go into the next section about Autodesk Moldflow. The Moldflow is look like this. This is the interface of the Moldflow. After we calculate all the setting, we will get the result, and we can see the animation. And every result on the left pane of the browser, we can click to see every calculating result and see and check the result on the model and cut section, everything to do the report. So that's getting us closer to the real world right way, easier than doing from the experience. You can see the Moldflow interface is quite easier to use. and then checking by just clicking on the model and check the value, and then the result and the process setting as well. Many settings, many factors in the software that we can extract to use in the real life. Okay, we can see the result of the conformal cooling, that how effectively they extracting the heat. Okay, we going to the next one is the net fab. In today's slide, we focus on the net fab. The net fab, how it look like. This one is the interface UI of the net fab. We can see that we can have clearly UI, and then we can easily use the software by setting the dialog. Okay, it's quite effective, but we don't forget in the fab yet. But I want to show you that we have the solution for you if you're doing the RP machine and want to produce the conformal cooling techniques as I presented in today. And this one we show in the real machine that doing the SLM technique. The roller will roll the powder in the bed, and then the laser shooting at and melting the powder to combine with previous layer. And the last one, Inventor, we have the CAM, and also Fusion 360 also have CAM. If you want to do the CAM or computer-aided manufacturing, both Inventor and Fusion 360 can do. But in today, I will present about the Inventor CAM. After that, after we doing CAM and everything, we making the mold completely, all the component, and then combining together and injecting the part into the mold and getting the result. The black one is a plastic part, and then we taking out all the component and then eject the part. And you see from here that the insert that we doing in RP and CNC machine, everything making our mold effectively cooling the part down. And then injection molding with conformal cooling, we have the full section, the design going to machining, and design going to printing, or design going to molding. Everything we can do all entire the process by our solution from Autodesk. In this one, I will show you about the process about setting the conformal cooling in Moldflow. That's quite easy way to use the software. Please see the video.
This shows you how to set up and run a conformal cooling analysis using CAD geometry that has been created in an external CAD package such as Autodesk Inventor. Before running a conformal cooling analysis, it is important to understand the major workflow that you will need to work through in order to set everything up correctly. The study tree illustrates the main steps that you must undertake to achieve a valid setup. These include importing the CAD geometry for the part and meshing it, setting the cool FEM analysis process, selecting a material, setting an injection location, importing the CAD geometry for your 3D cooling channels, assigning boundary conditions to the cooling channels, meshing the channels, and creating the mold block and meshing it. As you complete each task, a green tick appears beside the task on the study tree. Each task must be completed before the analysis can begin. So, to begin the setup process, first import the CAD part geometry as solid 3D. Next, you will create the part mesh. Ensure that you check the mesh settings prior to creating the mesh. Now select the cool FEM analysis sequence. Once you have selected Cool FEM as your analysis sequence, you'll note that the study tree now has some additional entries in it, for example, cooling circuits. Next, you should select a material and set an injection location. Now import your 3D channel CAD geometry. The Properties dialog shows that the 3D channels have been assigned the correct property of Channel 3D. Next, you must assign an inlet and an outlet boundary condition to the 3D channel. Note that the study tree automatically updates to show the number of inlets and outlets that have been assigned. You will also note that the green tick, which indicates a completed task, is not placed beside the task until you have assigned the correct number of inlets and outlets for your channels. Now you should create the mold block using the Mold Surface Wizard. Now you should mesh the 3D channels. Once you have meshed the 3D channels, you should mesh the mold block. This is a two-step process. First, you create the surface mesh of the mold. The surface mesh can be investigated to ensure that it is fine enough in critical areas of the mold. When you are satisfied with the surface mesh of the mold block, you should then mesh the volume of the mold. This will incorporate any modifications made to the surface mesh. There should now be a green tick against each task in the study tree, and Start Analysis is now available. You are now ready to run the conformal cooling analysis. There are a number of different methods that you may use to set up a conformal cooling analysis, and we have demonstrated just one of them in this video. When your analysis is complete, the following results are available for you to view.
Okay, we can see from that video about the easy way to use the conformal cooling technique in Moldflow. And then we go into the real life example, conformal cooling customer example. We have Günther Hoffman wants to validate the profile cooling channel before manufacturing. You can see from this picture. We try to produce the cooling channel look like this, and then compare between traditional method and the conformal one. We can see from the left picture is a conformal, and the right side is a conventional one. You can see that the cooling channel just goes straight and then back out. That's not quite effective way to do cooling. But the left side, the coolant will go into the part, and then complex helix shape can do better cooling. The condition is to evaluate the benefits of the conformal cooling temperature is what compare conventional one to cooling channel. But we can use both technique in the same part. Like in the first analysis, the needed cycle time to achieve the injection temperature 195 degrees centigrade was calculated. So this is the condition. So the workflow that we're gonna do, the first one is import of the CAD data. If we don't have the CAD data, the 3D CAD data, yes, we cannot go into Moldflow anyway. But we in this technique we cannot use. But we if we want to use this technique, we have to have 3D CAD first. And then the second step, it will be definition of the mold properties. And the third one is we do the meshing. We do the meshing in three things, the part, the cooling channel, and the mold component. And then the fourth step, we assigning temperature of the conformal cooling insert. And then the fifth step, we do the definition of the process settings. And then after that, we can run the analysis. If we have lost anything in the 5 steps before the 6th step, we cannot run the analysis anyway, because the software quite require the complete assignment before running the calculation. Otherwise, it cannot run. Okay. The import CAD geometry, we can see that we can import various types of file format. For example, in the STL one, we can also import the set file, step file, and the IJS assembly from the Pro-E or Creo, and the SolidWorks as well, and the CATIA. Many software or native file format can be imported in Moldflow. But anyway, we also have Inventor and Fusion 360. Both software can do the translation good as well, because they have the translation inside. And in the Fusion 360, we can publish all the part in the cloud. So we manage everything in the cloud. That's quite effective. We don't worry about the loss of the data. Not like offline managed system, like on the hard disk, that we have to take care about the hard disk. If drop the hard disk or lost the hard disk, we lost the data, but the cloud is not. Okay, and the definition FEM, we use the condition like this, and then we set all the thing to the every part, and then we matching all the part that the process that we can see earlier in the step before. And then after that, after matching, the software will mesh all the thing, not just the surface, but inside as well, because the software seeing the model like a volume. So everything in the volume had to be meshed. And you can see from this, the section way, and you see the 3D mold mesh as well. And the heat transfer, we set all the condition and the area that we quite focus on. And then the definition of the setting, everything. In this example, we use the A3WG6 material ultimate from BSF, and then set the condition 195 degrees centigrade is leach. And then after that, I will show in the video. Before, this one I did by myself, and then I explain everything from the fusion to Moldflow. So please watching this, and then everyone will know about from the CAD system to the Moldflow system, how to do it. Before we getting into Moldflow, so we have to create the model or open the model inside Fusion 360 first, because Moldflow cannot create model in itself. So we have to use the CAD system to create the model or fixing the model before sending to Moldflow for doing simulation. So we have two methods to do the export to Moldflow. The first one is right click at the model or the part and then export. This one we can create the name of the file and then the type of the file. So I use that file, and then I can click the location to put the file. So I use this C drive, and then I go to the Moldflow, and then I create the folder inside here, and then I export one by one into that folder. So this is the first method. The next one is when you install the Moldflow, it will create the icon like this. So you click the simulate in Moldflow inside here, and then the Fusion will communicate with the Moldflow and sending the model inside Moldflow. After Moldflow has been opened, you can create the project. So I name this project CCC for Conformal Cooling, and then I click OK. The project with this name already exists, so I change the name to CCC1 and then OK. Moldflow will create that for that project for us. Okay, after the model transportation process has been finished, so we can see this model completely inside Moldflow, and the layer separately created inside Moldflow as well. So you click the model and see. I can say that 100% completely imported into Moldflow. So don't worry about the error. Every model completely imported inside Moldflow. Like this. After I imported the model, so I want to rename because the name is not reflect anything. So I click here and rename. And then I rename this to Conformal Cooling Insert. And turn off this one, turn on this one. And this one is renamed to Core Insert. So this one I have to stop first because I will explain this. If you use the method of that button from the Fusion 360 inside Moldflow, the name we have to rename or something because it's used the assembly name to assign to the part. But if we use the exporting technique, the name will attaching to the part itself, and then once we import the name we don't have to rename. It depends on what the strategy you use. But I think the directly import from that button is quite easier for you. But you have to concern about the release or the version of the software is compatible or not. If not, that button will not occur, will not show. If the I use the Fusion update automatically, and Moldflow 2021, so that's compatible, be able to compare that, and then the button show in the software, so easier for us to import the model in Moldflow. And go to the next process for setting the model. And okay, then, okay, I will use this. Okay, I turn off the model first, and then I open the cavity and the core insert here, and the conformal insert here. Okay, due to the time is limited, so I will going into the setting, and then everyone can see the how to set in the Moldflow in this model. So I have to turn on these 2 layers, and then turn off this layer here. I flip it over, and then make the coolant channel 3D inlet to this location and this location, and then I change the outlet to this location and this location. After create the inlet, okay, we can see that this quite the same way that we have seen before. That we have to set every node to have the information. So the software will indicate by the green tick mark before the icon that we know that process had been set already. But if which one don't have, such as the set injection location don't have, so we have to set this first before running the simulation. That's the key point. So if we set everything, matching everything, then we can run the simulation. So I will skip to, okay, the next thing I want to emphasize is the material library in Moldflow itself. We can see that the manufacturer inside Moldflow is many manufacturers inside Moldflow. And we can do the cloud simulation as well in case of your machine is not fast enough to running the simulation. Frankly tell you that all the simulation software require powerful laptop or desktop computer to very fast to run simulation. Frankly tell you that. So you have another choice to use the cloud simulation by exchanging the cloud credit to the cloud. You pay this, and then you get the cloud powerful calculation. The benefit of this, you can shut down the machine off after sending the machine to the cloud already. So let's say, for example, if you want to doing the simulation at the 4 p.m. of the day, nearly to off the office time. So in normally local host or your machine cannot run because some simulation take time, right? And you close to the off time of the office, so you cannot do running the simulation. You have to go into next day, and then in the morning you running the simulation and wait. You have the time, right? But in the cloud it's different, because once you publish the model to the cloud, that's not take too long time. And then after that, you can shut down the machine and going anywhere, no problem at all. That's quite save your time. And then after the cloud finishing calculation, you can get that result from the cloud. That's the benefit of Autodesk that we provide for you. But in case you don't want to exchange your cloud credit, you have another choice by using your machine to run simulation. That's the choice. But you have to pay more money on your machine to make it faster and then launch the machine. In this case, I use my machine because my machine is quite fast enough. So I sending. Okay, again, we click the launch button and we wait for a moment. While the system generating the mesh, we can change the material by right click here and select material. And then we go to the BASF. we can search from the. We can see that the material in Moldflow as well. Many manufacturers be partner of Autodesk doing about the information about the plastic. So if we decide to use Moldflow, we can have a bunch, a ton of library of plastic that we can use inside. We don't have to rely on the lab or the provider, the vendor to provide us the information to put in Moldflow. But this one is quite effective way to use in plastic nowadays. Information here, BASF, and then we can see if we didn't see any decided trade name, we can search. Okay, we can see from here that the mesh failed because the mesh should be on visible layer. So we have to turn on the layer. Yeah, this is my fault because I forgot to turn on the layer, so the machine failed. That's not the software fault, my fault, okay? Because when you want to use the Moldflow, you have to pass the training class. That don't worry, we provide all the class for you. If you want to attend any class, you just tell the sales person and then contact, and we provide you all the training. Don't worry about it. And then after that, you can use the software confidentially. I-VTech insert, core insert. This 3 layer have to be on visible layer, and then we right click again, generate a mesh, and mesh again. So the system have the geometry to calculate the mesh. We click the launch button again, and then we go to the select material process. We change to the BASF as before, and then search. We can type the information of manufacturer, BASF, and then click search. And then the system will show you the information about the material. You can decide which one you want to assign to the part. In this case, we want to use the Ultra Mid A3W G6 and select. And this one will be assigned to the part, and click OK. After the mesh has been already created, so the dialog pop up, and then we click OK. And then we can see here from the screen, you can see the meshes all entire part or the mold part, and then we can see from the tick mark here, the indication indicate that all the process has been set. So the analyze turn green, or we can check from here the home button, the analyze button is turn on. So we can click here and the analyze process will begin. But before that, we choose save for making sure that all the process has been saved in our machine already. The cool, click the launch button. After the result from here. Okay, after wait for a moment or a while to calculate everything, the Moldflow will show the result in the left side. You can tick on any information and you can read from the screen on the right pane. You can see that using Moldflow is not that hard, so everything is easy to use, and then after that you can extract the information to use in your work. That's it. The important thing is the theory behind, because you can read the result and understand or not, that is the problem. So everyone should have the background of the plastic, and then can use the software effectively.
The result node, the cool and the warp section. First of all, I want to see, to make sure of that, we have to turn on all the layers, and then I open the deflection or effect deflection. To see the deflection after cooling by conformal cooling technique. You can see from here, the results have been shown like this. And then we can check, examine the result. We can click.
Okay, I will quickly present because the time is quite a factor. So everyone can see that we can get any result in the left pane, and then we can use, we can tick and see the result on the right pane and check, examine, or use the analyzing tool in the Moldflow to check. Okay, I will get to the result. The result here, you can see that the transient FEM technique that we get is better improved because the temperature decrease and the time also decrease. You can see comparison between conventional and the conformal. You can see the conformal one less red color on the insert or the part, but on the conventional you can still see the red area is bigger. That's quite reducing the mold life. Okay, and the time as well. And we can see comparison between the conformal and the conventional. You can see that the conventional is 174, but the conformal can reduce to 139. That reduce about 35 degrees centigrade. That's quite effective temperature. And then the cycle time as well, we can reduce from 12.5 to 8.3 seconds. That's I can show you the calculation about the percentage on this table. We use the 12.5 divided by 8.3. And also the parts per hour, we can increase the part per hour. You can see from 288 to 433. That quite amount of number. We can take the profit from one piece, right? Once we increase the piece and reduce the time, we can increase more profit. That's it. And then the deflection, the quality of the parts as well. You can see the deflection in conformal is just 0.34. But this one in conventional, you can see much more deflection occur on the part. That's not good. So we have this technique to reduce this. And then, okay, the next thing I want to talk about is a Moldflow for conformal cooling validation. So we can see from this, we use the cloud calculation. We can do this and all the information in this. Everyone can see and reduce the time in my present. Everyone already have that information. So the challenge, many of tool makers don't have metal 3D printing capability in-house. That's true. But I tell you that nowadays many vendors providing the 3D printing services. So you can hire that company to produce for you as well. So you don't have to take every machine into your house. So that's it. You can decide it, and the outsourcing of 3D printing insert is more preferred by tool maker than in-house manufacturing. That's I explained before. And though the conformal cooling insert provide more efficient cooling and reduction in cycle time, traditional cooling is preferred by tool makers. That ease of manufacturing, no need of specialist skill resource, and volume of the conformal cooling insert mold does not justify in-house investment. So the challenge is this. Okay, we're going to the last section, the setting that I showed you before, and the result that we're getting from Moldflow. Normally, we use three information: velocity channel, temperature channel, and the pressure channel. Okay, and the summary, optimized cooling is important, including quality, profitability. There are different ways to achieve this is more material, rapid heating and cooling that we can do in conformal cooling technique, as I shown you before. And with Moldflow, you can verify the right strategy early in the development process. Okay. Okay, how much time do we have, Charles?
I think we are just getting near the end of the session.
Okay, I will show you the last slide about the currently customer, the Fado, how they use the software, and this one about 5 minutes. Okay, here.
Fado is a company with more than 30 years of experience in tooling and injection molding. Our clients come mainly from automotive, electrical, and lighting sectors, but we also realize projects for other industry branches, such as consumer goods. Having both a tool shop and injection molding department under one roof makes it possible for us to offer complete molding solutions, from part design to production. We provide our clients with a vast range of services, including reverse engineering, simulation and optimization of injection process, as well as manufacture of prototype, pre-production, and conventional molds. While building tools, we combine traditional subtractive methods of production with additive manufacturing. For the last 4 years, we've been developing selective laser melting technology in the context of conformal cooling designs. Being able to use conformal cooling for our production purposes has been a huge asset, as it enabled us to learn the technology and understand its strengths and pitfalls. Cycle time is money. This is particularly visible in the case of high volume production, where reducing cycle times by a fraction of a second translates into viable profits. In order to reduce the overall cycle time, we need to decrease the cooling phase, as it is the longest process in injection molding and can take up to 70% of the whole process. The time we need to cool a part equals the time required to absorb the temperature from the worst cooled insert area. Thanks to freedom of design offered by additive character of the technology, we're able to create optimal cooling that somewhat follows the shape of the cavity while maintaining a defined distance from the molding surface. This is especially useful in the case of long sliders or cores, where conventional drilled channels cannot guarantee efficient cooling. Providing uniform heat transfer from injected parts not only reduces the cycle time, but also minimizes warpages and part deformations that might appear due to uneven temperature distribution. On the other hand, implementing conformal cooling is financially justified mainly in the areas that are beyond reach for conventional methods of production, or in the case of high volume production. It also takes some time to learn how to create channels optimized both in terms of cooling efficiency as well as insert maintenance and cleaning. We must remember that due to gradual scale agglomeration, thermal conductivity and cooling efficiency of channels will drop with time. That is why such inserts must be cleaned on a regular basis in order to prevent clogging or cooling efficiency loss.
One of conformal cooling application examples is a roller tube motor adapter, a part we produce for one of our clients. In this particular example, high ribs inside the part make it difficult to achieve uniform temperature distribution on the whole molding surface. Former solution was a spiral cooling insert coupled with a drilled cooling on the insert's bottom element. Such a solution was far from perfect, as a delta T for the upper and lower part of the insert was high above the acceptance range for semi-crystalline materials. Two conformal cooling designs were proposed. Although both guaranteed even temperature distribution, the second design generated lower pressure losses and was easier to clean. It is also a hybrid design. The bottom part was manufactured conventionally, and only the fragment which required cooling optimization was additively built on top. It enabled us to reduce build time and the cost of the insert. Optimizing the cooling design resulted in cycle time reduction from 90 to 36 seconds. In addition, we minimized the material waste from 9 to 0.15%.
Most of final part defects have their beginning on the early stage of product development and are usually related to insufficient verification of the design and technology concept. Preventive these actions after mold trials often means costly modification, necessity to accept some of part defects, or in some extreme cases, change of the mold design. Thanks to Moldflow simulation software, we are able to foresee potential problems related to difficult part geometries and counteract them at the early stage of design. In the case of cooling optimization, Moldflow coupled with our thermovision test bench is an important tool for cooling design and verification. Values obtained during simulation serve as reference point for the thermal behavior of the insert built in DMLS technology. Due to numerous factors influencing the insert quality, such as wall roughness inside cooling channel, simulation results obtained from Moldflow must be always compared with actual thermal behavior of the insert, flow rates and pressure losses for individual cooling channel. Only then we can be sure that our cooling design meets our expectations.
Okay, end of my slide shows. Okay, over to you, Charles.
Thank you, Sutan. So it was a wonderful presentation. I hope everyone could grab an idea of what Moldflow could help in conformal cooling aspects. So Icho, I'm calling out to you for the Q&A part. Hi, everyone. So if you have any queries, you can unmute and you can speak, or alternatively, you can use the chat box or the Q&A box to drop your queries.
Okay, any questions? If there are no questions, after the session, we will have the poll, right? Or the questionnaire, right, Charles?
Yes, there is a survey which will be taken, which we'll be taking after the session. So once the session is over, you'll be having some questionnaires. Request you to kindly fill in that so that we can also understand the feedback, and we can also check on any separate sessions or queries you want.
Mm-hmm. Okay, seems no question in this session, so I shall you?
Yeah, I have put my email in the chat box. So if you guys have any skills related inquiry, queries, or more about not only just Moldflow or any other Autodesk solution, you guys can reach out to my email. It's echow@innoventure.com, which is in the chat box. We'll also be taking any questions verbally or here live. So do you guys still have any? Presuming it's past lunchtime now, so
yeah. Okay, I think Ichao, there are no queries. It seems we can take it offline.
Sure.
So thank you everyone once again for joining the session. And I guess there is one query. Is it possible to share your presentation? Yes, Estira. So we will help you with the presentation recording. So we have the session recorded and we'll share that for you.
Okay, thank you very much, everyone. We have this session recorded, so we can share the video to you.
Correct. And besides sending them out personally, it will also be streamed on our I-VTech Facebook. So do keep a lookout for it. And we will also share the link to that Facebook video, a Facebook link on our LinkedIn also, if that's your preferred social media. So do check out our social media pages, I-VTech Solutions on both LinkedIn and Facebook. Yeah, that's pretty much from our I-VTech end. So yeah, thank you, Suton, and thank you, Charles, for coordinating all this.
Thank you all. Wish you a great day.
Okay, thank you, Yichao. Thank you, Charles. And thank you, everyone.